Institute. He obtained his college degree at the University of Belgrade, Serbia, and his PhD at Cornell University in Ithaca, New York. He was a postdoctoral fellow at University of British Columbia in Canada and at Harvard University and Smithsonian Astrophysical Observatory, both in Cambridge, Mass. He specializes on modeling orbital and rotational dynamics of the solar system objects with a focus on planetary satellites and asteroids. He was the recipient of the 2014 Harold Urey Award by the American Astronomical Society, and asteroid 5639 Ćuk is named after him. We think that the moon formed in an ancient collision between the young Earth and another proto-planet. However, the standard giant impact theory predicted that the moon should be made from the pieces of the other planet, while lunar samples suggest that lunar material is very Earth-like. Our speaker will talk about some recent updates to the giant impact theory and will present some of his own work on the orbital history of the moon after its formation and how the Earth could have lost some of its original spin in the process. Join me in welcoming our speaker tonight, Matija Ćuk.
Thanks, Linda, for inviting me, and also for introduction. There were spoilers, but I'll go in more detail. So I don't know if I have material to talk the whole hour. Anyway, not all my slides are necessarily public friendly, so please do ask questions throughout. That way we're all going to get more out of the talk. The talk is going to be both about formation and tidal evolution. My work has mostly been on tidal evolution, and I hope to convince you that it's the crucial part of the history of the moon that we need to understand before we can understand formation. So, in a couple of days, it's going to be 50th anniversary from the first moon landing, and so for planetary scientists, the moon landings were not just about planting flags and having firsts. Actually, the biggest influence on planetary science for moon landings was the samples that were brought back to Earth. And here's another rock, I think, from Apollo 14. So I'm talking about how we still don't understand how the moon formed, even after getting samples from the surface. Imagine how much worse the situation would be if we didn't have samples. We would not know how much we don't know, but now at least we know what the problem is, and we're trying to solve it. So I'm going to tell you, what the standard picture up to about 2000 about lunar formation was, why it needs fixing, and what the possible fixes are. Some are mine, some are of other people's. Okay, so tidal evolution. I told you I'm working on lunar tidal evolution. So what do I mean by tidal evolution? This applies to the moon and many other satellites in the solar system. Here I'm talking about the moon. That whenever a satellite is orbiting a planet that is spinning faster than the satellite orbits the planet, you have gravitational interaction between the satellite and the planet that deforms the shape of the planet, makes it kind of egg-shaped. If the planet is solid, it just means that the rock deforms a bit. If the planet has an ocean like Earth, that means that definitely the water wants to make a bulge underneath the moon and on the opposite side of Earth. This is a symmetric effect. Now, if the planet was exactly elastic, which means that it just changes shape according to the outside forces without losing energy, the direction of the long axis of the egg would always point towards the satellite. But it's not in real life. No material is perfect, so it takes some time for the material to reshape into the new shape as the mutual positions of the satellite and the planet change. And they always change the same way. The planet tries to spin out, so it's moving. I drew it spinning counterclockwise. The satellite is also going counterclockwise, but slower. So the shape is a little bit out of sync, and the bulge wants to get ahead of the moon because of the fast rotation. So the bulge itself then pulls the moon forward. In orbit, if you push or pull the body forward, it's going to move to a higher orbit. And much of what I'm going to talk about concerns the conservation of angular momentum. It sounds scary, but it's It's kind of physics way of keeping us honest. That's roughly the amount of spin in the system. And through this interaction, you can see that the moon is gaining the spin, angular momentum, by getting bigger orbit. But what happens with the planet is being pulled back by the satellite, and it loses spin. So one body gains, the other loses. And over time, the lunar orbit expanded from being about 3 Earth radii, which means that Earth and the moon are really close together, to 60 Earth radii, where it is now. So the moon is pretty far from Earth compared to other planets and satellites in our solar system. And this acted over billions of years. Much of it happened early on, and then this process slowed down. So much of the crazy early stuff I'm going to talk about happened in the first million years or tens of millions of years. Okay, so this is what I mean by tidal evolution, the constant drift of the moon away from Earth. Okay, so the first scientific really thinking about lunar formation was in 19th century when George Howard Darwin proposed that the moon was split from Earth, which would explain why the moon has lower density. Even then they knew that it has more rock and less iron. Iron in Earth is in the core, so if you split the piece of the mantle of Earth, you will get a body that is mostly rock and consistent with the moon. By the way, George Howard Darwin was the son of Charles Darwin, so it's the same family. Now, there is a problem with this idea, and that's that the moon, that the Earth never span fast enough to fall apart due to centrifugal force. So I told you that the moon keeps gaining orbital height, while Earth is losing spin. That means its spin period is getting longer. So originally, you can just kind of play back the tape and see when the moon was really close to Earth, what the Earth spin period was. It was about 5 hours. It's kind of basic physics, and 5 hours is not fast enough for Earth to fall apart. So body with the material, Earth-like material, can spin about once every 2 hours and still stay intact. Like the gravity is still stronger than the force of the centrifugal force that pushes it apart. Also we knew that the moon could not just be another planet that was captured intact. Physics of capture aside, an independent body would generally have about a third of it be a core. That's how Mars is, that's how Venus is. Okay, Mercury has a little bit bigger core, but nothing is really that much rock and that little iron as the moon. So it doesn't seem to be independent of Earth. Something special happened to make the moon. This situation lasted until '75. That was after the Apollo landings, when the giant impact was proposed by 2 groups independently. Original giant impact had the moon forming, Earth and the moon forming from a collision of Earth and another large object, maybe the size of Mars. So if you take away one thing tonight from this lecture, that is that the giant impact is not a one-off kind of strange event. That's how it was proposed. Back then people thought that giant impacts are rare, and maybe moon being so weird needs a special explanation for why we have it. But since then, especially using computers and computer simulations, people have realized that when you put together solid planets like Earth, Venus, Mars, you start with relatively small bodies that kind of look like asteroids, and then collide and merge, and then you end up with bodies the size of Moon and Mars, which fly around. There are fewer of them, and they take millions of years for them to collide into bodies size of Earth. And always in the end, there'll be one giant last impact where Earth kind of absorbs the last remaining piece of matter living along its orbit that still crosses the orbit of Earth. So throughout this story, I'm going to tell you all things that are wrong with the giant impact, but it's not unlikely, it's not one-off. There should be giant impacts, and planets the size of Earth and Venus should have experienced giant impacts in their history. Body size of Mars, for example, that didn't have to, so that's a whole different story. But to make something size of Earth, you have to put together multiple planets. Okay, so circa 2000, the idea behind the standard giant impact. So that's not exactly the same as proposed in 75, because since then people have done numerical modeling, which kind of checked out, and we had a pretty good idea of how the giant impact worked. So you have a collision between Earth and a Mars-sized object. It's a kind of a slow collision. They barely come together, and then they attract each other due to gravity and collide. The impactor, the smaller body, is completely destroyed, and the material from the impactor goes into orbit around the Earth. Some of the material goes to orbit around the Earth, and then this disk, after a while, condenses into a moon. Turns out that the material in the disk. You have a question?
What does V space I have?
V infinity. That means what was the velocity of the impactor when it was very far from Earth. So, because the planets attract each other by gravity, when they're far apart, they move at one velocity, and then as they come together, they're going to move faster and faster. So V infinity is kind of calculated how fast they would go if they were like really infinitely apart.
Thanks.
Yeah, and that.
I have my own theory.
Oh, no. Yes. Okay, so this is a computer simulation by Robin Cannon. She was kind of the biggest authority on classic giant impact, and really moved it from an idea to a well-developed theory. So this is from her review paper of 2004, which is basically kind of state-of-the-art at that point. And the interesting thing here is that you have the impactor Earth. This is the moment of contact. I think the color is just how shocked the material is. So the Earth stays more or less intact, but the impactor is completely destroyed, gets pulled out into a noodle, and then the material goes around eventually to form a disk around Earth. So the important part for this talk is where the material that goes into disk around Earth comes from. So what Robin Cannon did here is, when she got the disk in the end, then she went back, traced her particles. So this is kind of SPH, smooth particle hydrodynamics simulation, where both the Earth and the proto-planet, the other proto-planet, are made of discrete particles. And when in the end you get a disk around Earth, you can go back to the beginning and ask yourself, where were the particles that ended up in the disk? Where did they start from? So the disk particles are yellow. The red ones escape the system. So you can see that at the moment of at the point of contact, the stuff was really blown away really fast. But then a little bit further from it, much of the material that ended up in the disk, most of the material that ended up in the disk came from the impactor, not the Earth. So why is that important? Well, actually you can tell apart, using lab analysis, you can tell apart different planets. Like if you have a meteorite, you can tell if it's from Mars. And one of the, originally, it was complicated until we had one that we knew it was from Mars. But then you get a new one, you can compare it to the old one and say, oh, what is the oxygen isotope signature? So these are geochemical plots, which I don't quite understand myself because I do orbits. But it tells you in a very strange units how much oxygen 17 and oxygen 18 relative to oxygen 16 there is in the body. Now when you think of oxygen, you think of gas, right, that we are breathing. But basically every rock contains oxygen to some extent, like just the minerals contain oxygen. And the most common isotope of oxygen is oxygen 16 that has 8 protons and 8 neutrons in the nucleus. But sometimes you have oxygen 17 and 18 which have 1 or 2 extra neutrons. And how much extra neutrons you get on average depends on which body the material came from. So this horizontal line is terrestrial fractionation line. So basically that's Earth material. And then you can see that different planets have different have their material be along different lines. Same in oxygen 17, but with a range in oxygen 18 content. The moon is exactly on the same line as Earth. Now, here's Mars. These are Martian meteorites. These are eucrites. They come from Vesta. So basically, this is the line. This line corresponds to a large asteroid Vesta, which is kind of like a planet because it has a core and a mantle and all that. And angrites are an obscure group of meteorites that come from a planet that doesn't exist anymore, that existed in the early solar system and was destroyed, similar to the proto-lunar impactor. But some pieces of it still live somewhere among the asteroids, and we get them as meteorites. So you can see, like, you can generally tell apart different planetary bodies based on the oxygen isotopes. And turns out, whatever element you take, you can tell by looking at the isotopes. So this is how much titanium-50 you have relative to the other titanium. This is I forgot what SN is. What is SN? Any chemists in the audience?
Strontium?
I don't know. But the people who do this have looked at all the isotopic systems, and you cannot tell Earth and the Moon apart. And that's really weird, because you can tell other planetary bodies apart. Sumerian, that's right. So this is a relatively recent paper from 2012. But they just keep adding new elements, and they keep, Earth and the Moon are the same, but other planets are different. Now, tungsten isotopes are very interesting. Unlike oxygen and the other things I showed you, tungsten is partially radiogenic. That means that one kind of tungsten, 182, is obtained by the decay of hafnium-182. So why do we care? Well, tungsten wants to go into the core. That's what radiophile means. That's just a fancy word to saying when you take a planet, melt it, iron goes into the core because it's heavy, rock stays on top. These minor elements, depending on their chemistry, they want to go with the iron or stay in the rock. Tungsten wants to go with the iron in the core, but hafnium doesn't. But hafnium turns into tungsten over millions of years. So by looking at the signature of hafnium, it's not just the provenance you get, but also how things changed over time. And Earth and the Moon are the same. So even if you made them from the same material, if they did not evolve the same way, you wouldn't get the same signature. So it's not just that Moon is Earth-like. It's made from Earth material. So people were getting uncomfortable because people kept saying, well, we'll improve analysis, we'll find the difference. It's just a matter of shrinking error bars. But it wasn't happening. So people call this isotopic crisis of lunar formation. That we had a model, it predicted that the Moon is made from a planet, basically mostly made from a planet different from Earth. As far as we can tell from the sample analysis, it's not true. And then there is this issue of orbital inclination. I'll talk about that more. So everybody was talking about the composition, and since I do orbits, I was always talking about orbital inclination. And those two might be related eventually. Okay, so the first stab at solving this problem of lunar composition was people saying, well, we had this disk around Earth, and maybe it was made of molten, vaporized rock, really. Earth had a vaporized atmosphere for a short time, and the disk itself was vaporized rock. Maybe this vapor was mixing, and that way you got the disk and the Earth to have the same makeup, and then after that you make the Moon from the disk, and it's same as Earth. The problem is if you start mixing them, there'll be friction, and the disk itself is going to fall onto Earth. And Earth is not spinning fast enough that it cannot absorb the disk. So that was the biggest problem proposed with this first equilibration proposal. Now this will come back in a different form later, but the idea is why this shouldn't work is that the disk is spinning faster around Earth than Earth does. So that's an important thing. Like, if you are in orbit around Earth, say space station, right? It goes around once every hour and a half. So Earth at that point was spinning once every 5 hours. So the disk on the inner edge of the inner edge of the disk, material was going around also an hour and a half, something like that, while the surface was going around once every 5 hours. So whenever there was a contact between them, the material would slow down and fall. And the amount of material and spin in the disk was not enough to make Earth fall apart. It would just absorb the disk and continue spinning at 4 hours, something like that. So you can see a kind of recurring theme here. Darwin Jr. had this problem. Earth was spinning too slowly. Then if you want to mix up the disk and Earth, Earth is spinning too slowly. So why can't we make the Earth spin faster? And sometimes, yeah?
It says higher angle. Mom, I know what angle means. I know that angle means angle. But what is where?
Angular momentum, sorry. That's, once you've said angular momentum too many times, you see it everywhere. Yeah, so that's the amount of spin. So can we make this Earth spin faster? And the problem is that the first slide I showed you with Earth spinning down and lunar orbit growing, you conserve angular momentum. So if you conserve angular momentum during tidal evolution, that what we have now is what we started with. So that's a bit of a problem. So we are restricted in how fast Earth could have spun with the amount of angular momentum we have now. Okay, so, but it didn't stop us from trying, doing computer simulations. And Sarah Stewart, who was my postdoc supervisor at the time, and I tried doing simulations with a much faster spinning Earth. So Earth was very fast spinning to begin with. It's hit by a fast object, and Earth is like heavily, so these are just snapshots from the simulation. Earth is heavily damaged, material flies all around, and then gets back into the circular shape. And what happens here is the material, because Earth is heavily damaged, and because of the spin, it has much harder time retaining material. The material in the disk ends up being mostly from Earth. And when we make this same plot that you saw before, where we project the final fate of the material onto the original bodies, the red escapes. So you can see half of the impactor is blown away, basically. But material that goes into the disk is mostly from Earth, from the side that gets hit. And also at the end of the simulation, Earth is spinning too fast. It starts out spinning too fast, it ends up spinning too fast. So we can make Earth like Moon, but we have Earth that spins too fast at the end of this collision. So that's, oh, sorry, I should mention that there are other ideas kind of very similar. This one is by Robin Canna. We had a fast spinning Earth hit by a small impactor. Here, Robin Canna proposed two similar sized bodies hitting more slowly. Since they're symmetric, everything is symmetric in the end. So the disk ends up being an equal mix of the two. I won't talk much about this, but that's another way of getting Earth-like disk around that will form the Moon. This model also ends up with Earth spinning too fast. So the problem is, how do you slow down the spin of Earth? So we looked at a couple of things, so first I'll tell you the original paper, about the original paper. That was so-called the evection resonance. Don't be scared, I'll explain what it is. And then later I'll talk about quasi-type perturbations with high obliquity. That is even more scary, and I'll try to explain what it is. My own colleagues had heads get kind of spun around, and you know, sometimes the truth is complicated. But first, the original paper. Okay, so this is a Ptolemaic view. So I'm not claiming that sun goes around Earth, but it's a convenient way of looking at the problem. So everything goes counterclockwise. So the motion that's interesting here from the point of view of the sun, is not lunar orbit, which is very fast. This was early on when the moon was spinning around Earth every few days. But the whole lunar orbit moving around, the ellipse itself, is moving in the same direction as orbital motion. And the period with which it's going around depends on how close moon is to Earth. So early on, the orbit was spinning around like crazy because it was close to Earth that had this large equatorial bulge due to high spin. As the moon was moving away, this motion of the orbit that we call precession, the rotation of the whole ellipse of lunar orbit was slowing down. And at some point, it hit 1 year. So it was in sync with the sun. And that's why you can have strange interaction, where the angular momentum can be lost, because you open a channel through this equal period. And when you have equal period, we call it resonance. Through this resonance, you open a channel by which you can transfer angular momentum from orbit of the moon to the orbit of Earth around the sun. So then this angle between the lunar ellipse and the sun can get fixed for a while. So that's what kind of happens in the real space. In science papers, we just plot strange orbital elements. This is kind of distance of the moon from Earth. Ignore everything else. This is the good one to look at. So the size of lunar orbit grows until it hits this resonance, then it stagnates for a while, even moves a bit closer in, and then resonance breaks down for complicated reasons, and the moon moves out. So the moon is stuck for a while at a certain distance from Earth, and during that time, spin period of Earth gets longer, and we end up with a spin period over 5 hours at the end. In the course of all this, the size of orbit around the sun gets slightly bigger, but like by 1 millionth part. So we don't really worry about that. So this worked, at least math worked out, and that kind of opened the whole problem again. In this, the model that we did, doesn't matter what we assume for the properties of Earth and the moon, or what the original spin period is, we always end up with the current amount of angular momentum. Don't worry about this. This is kind of, don't worry about this either. So what it says is that math works out, but works out if we assume certain things for the relative strength of tides within Earth and the moon. And many people will tell you it's not the right thing to assume, and but with these assumptions, it does work out. But although this is kind of the most famous thing I ever did, I was not happy because there was this thing of lunar inclinations. Lunar inclination. So what is lunar inclination? Well, think about this. The moon goes around Earth, and at new moon, it's between Earth and the sun. But we don't get a solar eclipse every new moon, because moon is usually either above or below the plane of Earth's orbit. So lunar orbit is actually tilted by 5 degrees to the orbit of Earth around the sun. And both planes dance around, and sometimes we get eclipses, sometimes we don't. But there's a problem with there being this tilt. In the previous slides, I told you about how the moon formed in the disk around Earth's equator. It was not as flat, probably, as Saturn's rings, but that's the idea, that it was right around the equator, and when you make the moon, it's going to be in the plane of the equator. Orbit gets bigger, but it should not get out of the plane. At some point, we move out from the plane of the equator to the plane of the orbit around the sun. I'll have a slide later on that. But everything should stay in plane. You should not have this tilt. And 5 degrees, for at least for astronomers, it's a lot. And then came this paper. There was a grad student at Santa Cruz a few years back, Irina Chen, and she did some work on the tidal heating within the moon, and found out that people have been ignoring this one kind of interaction between Earth and the moon, and that pretty much everything we did on lunar tide evolution, including my paper I just showed you, is kind of wrong. So this was amazing. At this point, I was working on this for 10 years. And why didn't I catch it? Because I thought, well, people have looked at it and nobody's found anything, so clearly there was nothing to find there. So that was a lesson for us all. So back to the drawing board. So basically what this means is that lunar inclination has shrunk over time. That's basically what it means. What we see now as 5 degrees was larger in the past. Okay, so I told you I would explain what it means that the plane of the equator changes into the plane of the orbit around the sun. So you have a planet with some obliquity. Obliquity is how much is tilted from upright. And close to the planet, the satellites follow the orbit of the plane of the equator. Or at least disk would follow the plane of the equator. And then moon forms from the disk, and as it moves away, its kind of reference plane would smoothly transition from the equatorial plane to the plane around the sun. Why does it care about equator or the orbit around the sun? Well, these planes are basically what perturbs the orbit, what tucks down the orbit. And close to the Earth, it's the fact that Earth is not round but has this equatorial bulge. Far from Earth, it's the sun as a third body is what makes the orbit perturbed and serves as a reference plane. Okay, so this is what happens when the tilt is moderate. But what if you tilt the planet very, very high, like Uranus or something? At some point, you don't know which way is up, which way is down, because it's not clear if you're spinning clockwise or counterclockwise. So there is a chaotic region. Like these two planes are not connected. When you have orbits around the equator and the moon gets bigger and moon's orbit gets bigger and bigger and gets beyond this zone where Earth's equator dominates orbits, you are in kind of undefined zone that you have to cross until you get to the zone where the sun dominates. And this has also been found only recently because nobody really looked that much on highly tilted planets. And the math is just horrible. There is a reason why they are computers, so you should stick with that. So we realized that this undefined zone is great because just like I told you about the resonance before, it opens a channel between Earth and the lunar orbit and the sun where you can lose angular momentum. This chaotic zone is the same because you have complex interaction between Earth, the moon, and the sun. And the usual rules do not apply in this chaotic zone, and you can lose angular momentum. And what also happens, okay, these are horrible plots that we put in a paper. The moon goes up to this distance of about 17 Earth radii. Sorry for the colors. And it gets stuck for a while, then there drops in, comes back. This is the chaotic zone, basically, what I showed you, where there is the distance at which the zero inclination is not well defined. So the moon gets stuck there because its orbit gets eccentric and inclined. Okay, this is the real way of plotting it. But at the end of all this crazy evolution, the angular momentum drops in our units, and the red line is where we need it to be to get to where we are now. We get close to that. And the lunar orbit, when we are done with all this, has inclination of 30 degrees. So I told you that yeah.
I wanted to step back to the Uranus example
Yeah.
you're talking about. Are the orbits of the satellites in Uranus really screwy compared to Earth?
No, because there's nothing in this chaotic region, really. So the regular satellites, Miranda, Ariel, Umbriel, Titania, Oberon, are all here, closer than the chaotic zone. And then there are these captured satellites. There are 6 of them or something that are orbiting far away.
But so they orbit around the equator in Uranus, even though the equator is kind of...
Yeah, they don't care about the rest of the universe.
Okay.
Like it's equator of Uranus that really governs their motion. And then each other a little bit, but not the sun, really.
So it's not weird like planet Pluto's 5 satellites where it's like the law of the jungle in terms of what the satellites orbit.
Well, Pluto's satellites are the same. With Pluto, it's Charon that they care about.
Right.
The other 4 care about Charon. And then the sun is too far to really matter. So what people have done, Dan Tamayo, in his paper, they looked at dust. If dust falls from the satellites that are out there then it gets crazy. And the dust orbits can really do weird things. Yes?
You didn't finish your thought. Do the captured satellites also go around the equator
No,
of Uranus,
no.
or they go around the plane of the solar system?
Well, their orbits are kind of in terms of how their orbits evolve, they recognize the plane of the solar system, the plane of Uranus's orbit really, as the reference plane.
Okay.
However, they are not flat in the plane because they were captured. So they started out inclined. But in terms of their day-to-day dynamics, they do recognize the sun as the major perturber. Yeah, so if we assume that Earth started out with high obliquity, we can produce highly inclined lunar orbit. I'll get to later why now we have only 5 degrees inclination. We can lose angular momentum, and we can lower the obliquity of Earth. So the gray and the gray and the black lines are different assumptions in the model, and we can go down to 20 degrees obliquity, which is what we need to have Earth. And this kind of makes more sense than the classical idea, because in the original giant impact, the impactor has to come in the plane of Earth's orbit to give us the right obliquity. Because over time, obliquity in the original model grows. So we have to start out with obliquity below 10 degrees. Now it's 23.5. So you have to start below 10 degrees to end up where we are now. So this is one of those unfortunate things with so-called anthropic principle, right? You've heard of it. That's when people say, oh, well, why are things the way they are? Well, humans would not be on Earth if things were any different. So if the impactor did not come from a certain direction, then the seasons would be extreme. We wouldn't have mammals, humans on Earth. But then, problem with that explanation is that it's impossible to prove it wrong. So this is alternate explanation, that actually obliquity was much higher, and this special process brought it down. The interplay between low orbit of the moon, Earth's obliquity, and sun's perturbations. So even from the standards of orbital dynamics, this is hard to understand. Pretty much the only way to follow it is orbital dynamics, and is computer simulations. So what happens afterwards is that lunar spin axis. Only one plot on this, and that's enough. So I told you that Irina Chen from Santa Cruz has found that everything we did on tidal evolution was wrong. So the reason for that is that there is a period that's later, after all of those I showed you from the early system, where the tilt of spin axis of the moon was high. And it has to do with how fast the spin axis spins around relative to the orbit. And this has been known for a while. But what people haven't realized, it has a back reaction on the lunar orbit. So during the time that the lunar spin axis tilt is high, that means the moon is spinning basically spinning like Uranus for a short time. The tidal interaction of Earth with the moon can shrink the inclination of the orbit of the moon and bring it back into the plane. So that just tells us that the tilt of lunar orbit to the plane was higher early on than what we see now. And this is one of our simulations. So we start with a tilt of 30 degrees and end up with something below 10 degrees, and eventually it evolves in 5 degrees down. And during this time, we got interesting results that actually the moon does not turn the same side to Earth during that period. Because after all, if you're spinning on your side, what does it mean to turn the same side to Earth? Because the tilt is too high. Okay, so this is not the only explanation for lunar inclination. We try to fold it in with the composition of the moon. So Paul and Morbidelli, a few years back, also in a Nature paper, proposed that maybe flybys of other planetesimals have tilted orbit of the moon. Basically, you had all these protoplanets flying around early on, so every time something flies by, it messes up lunar orbit a bit. So after a while, you might get something that's tilted. We don't agree with this, mostly because we think that the orbit of the moon should be more out of round. It is more eccentric than it is now from this method. But we are still all working on this. So this is another possibility for generating the inclination of the moon. But also you have to assume that the moon hasn't lost much inclination since, which requires the moon to be very rigid during its high obliquity phase. So all these things are related, and it really depends on what you assume, and it's all very complicated mathematically. Okay, so there is another much more simple proposal to explain the similarity of Earth and the Moon. That is that, okay, we have Mars, we have Vesta, we have a couple of other asteroids, but we do not have samples from Venus or Mercury. It's very hard to get meteorites from Venus, and also from Mercury. Mercury is much closer to the Sun. And as for Venus, even if you have a big asteroid impact on Venus, atmosphere is very thick. So rock being launched from the surface of Venus has a hard time getting out. So what if those are the same as Earth? Maybe a large chunk of the inner solar system is the same, and we just see that as the similarity between the impactor and Earth. So the only argument you can have about this is, you have a computer simulation and you try to make Mars and Vesta different from Earth, but Venus and Mercury same. And people argue that that's unlikely. Not impossibly unlikely, just unlikely. So it all comes down to how comfortable you are with going for low probability things. Yeah, everybody thinks that their stuff is likely and that other people's stuff is less likely. That's how I understand. Yeah, so the argument, another argument against that is that I showed you that one of the isotopic systems in which Earth and the Moon are the same is hafnium tungsten, and that hafnium turns into tungsten over time, and tungsten wants to go to the core, but if you inject it in the mantle after the core was formed, then tungsten ends up in the mantle. So the amount of tungsten in the mantle gives you also the time when the core formed, and that means that it's not just the material that's the same for Earth and the Moon, but also their history. They share the history. So wider homogeneity is, would not give you the same hafnium tungsten signature. Of course, until we have a piece of Venus, we can't really say if it's true or not. So another interesting proposal by Raluca Rufu was that there might have been multiple moons. So, there are multiple impacts. You get mixing of material, so kind of homogenization after a while of material. Like multiple bodies contribute to Earth, but multiple bodies contribute to the Moon. So this is something people are still working on, but there's also argument about, yeah?
What are the years? I see that in times you have like centuries, meters, days, centuries.
Mega years.
Mega years.
Mega years are millions of years.
Oh!
So, yeah, so we like talking about kilo years, mega years, and giga years. So it's like kilobytes, megabytes, gigabytes, just
Oh, I
years.
understand. It's in the metric system. It's just they saw meters or like
Yeah.
currency. What?
Yeah, so unlike in kilobyte, kilo year has 1,000, 1,024. Yeah, so this has to be still worked out. So it's so far people don't think it naturally gives you the answer, but clearly it's more complicated. And on some level it's true, because we didn't have just one giant impact. Okay, maybe one was more important than others, but there certainly were other impacts putting together Earth. So that's something people work on, but so far hasn't given us a kind of a clear solution. So another thing people looked at was, okay, Earth and the Moon are the same isotopically, but are they chemically the same? Well, not exactly, because some well, when I tell you that they're isotopically identical, it has to, I'm talking about things that are so-called refractory. They do not evaporate easily. When you look at things that are so-called volatile, which are easier to lose when you heat them up, there is a difference. And that's where people say, well, it looks like material that made the moon was very hot at some point. And that's evidence for very fast impact. Okay, so the latest thing that I was kind of tangentially involved is the proposal that actually making the moon is more complicated. That we've been talking about this disk made of vapor, but disk is really mixed in with the planet. And especially if the planet is spinning very fast, there is not real boundary between disk and the planet. So this is from a paper by Simon Locke that came out, I think, last year. So this is how fast the planet is spinning. So on the bottom are fast spinning planets, on top are slow spinning planets. So these are all pure simulations, kind of a slice through the planet. When you spin it up and you heat it up. So from left to right is the amount of heating of the planet. Here it says entropy, but it's basically heating. And you can see that in this corner, you have a round planet with concentric layers. And on this corner, when it's fast spinning and hot, you have this thing coming off the planet in the plane of the equator, which is basically kind of spun off hot disk. So you still need an impact to spin up the planet and eject some material, but you can see that the planet itself, until it cools down, will not have the disk fall back on it. So that was the problem with the original mixing, that the planet can reabsorb the disk. But if planet is really hot and spinning really fast, it will not reabsorb the disk because the disk wants to go away because of pressure and also because of the spin. So maybe everybody's kind of right in the sense that, okay, you form the disk mostly from Earth, if Earth was spinning fast, but even the difference between the disk and Earth can be smoothed out because now the disk is stable, it will not fall back, and has time to mix in with Earth further. This has to do with the orbit of the disk. It's really not that important. Well, you know, the people have written, well, Simon Locke has written a PhD literally about this, so you know, there is lots of stuff there. But I just want to give you a flavor of everything. So the main point is that giant impacts is here to stay, but not exactly the way we thought it happened, because the original version kind of implied that the material must have come from the impactor, and that's not true. So we need to revise it. Also the other problem that I am much more concerned about than most people, because I work with orbits, is that the past inclination of lunar orbits was really large. And that just tells us that it's not, you can explain with a fix. Something very fundamental about formation of the moon, entitled evolution, was not in the plane. You have to think of it as a 3D problem. So I told you about that, you know, different solutions, that you can have mixing, you can have isotopically similar impactor, you can have Earth with high spin, and you know, I'm pushing towards the Earth with high spin because I was working mostly on that. But only by taking all of these constraints and testing both the composition and the orbit, so the chemistry and the physics, we can actually move forward. Okay, so the giant impact is here to stay, but we cannot, no, we have to move away from the classic picture. It cannot be improved with minor fixes. We have to realize that major fixes are needed. So this is not something that the public really needs to be told, but this is more for the scientists, actually, that I've been giving this talk to before. That people are comfortable with what they had and want to just tweak it. Well, lots of things are wrong quite a bit, so we need to make a major changes. Thank you.
So I realize the orbital dynamics are quite complicated, but could you explain once again why you think the Earth lost its angular momentum? Where did the spin go?
Okay, in every mechanism, so I showed you two. The spin actually goes, angular momentum goes in the orbit around the sun. So orbit around the sun gets a little bit bigger because Earth system has lost its angular momentum. And in cases where also Earth is tilted, that means the orbit around the sun gets tilted slightly. Those are like 1 part in a million, because just the orbit has so much momentum compared to spin. Does that help? Yeah.
Earth's on a wobble on its axis for
Yes.
something like 26,000 years.
Exactly.
When the spin was much faster, how would that have affected the wobble? And also, would that affect how satellites like the moon would orbit around the planet?
Yeah, so the wobble went much faster for several reasons. The faster spin actually slows down the wobble because there is more inertia to the spin. But two things speed up the wobble and win. One is the fact that Earth is more fat at the equator. So the moon is tugging at the equatorial bulge, and the torque is stronger. And then the moon is closer in, which makes the forces faster. The wobble at first was not faster than 1,000 years. So that's much faster than all the other things I showed you. Like lunar orbit goes around, the precessional lunar orbit is year to 10 years, up to 100 years. It does, there are some, there is some interesting interaction between the wobble of Earth and lunar orbit in the high obliquity case, and that's what causes Earth's axis to like straighten up in the plot I showed you. So you can get, in the 3D case, in the high obliquity case, you can get some interactions between
Does
lunar
that have an
orbit.
effect on inclination?
Sorry?
Does that have an effect on?
Yes. For all these, you have these vectors in 3D, for everything to work out, that means that you don't lose any momentum in 3 dimensions anyway. You have to create lunar inclination when you're straightening up Earth. Yeah?
Does the model effectively guarantee a tidal lock? And if so, do other binary tidally locked systems tie back to this model?
No, so tidal lock is kind of a basic outcome of tidal interaction. Whatever you do to the moon, it will slow down its rotation and eventually get locked, as long as you have tidal forces slowing down the spin. So what I showed you there in the first slide was that Earth's spin slows down due to lunar tides. So originally, when the moon was spinning faster, Earth's tides slowed down lunar spin too. So it was a symmetric effect. The only difference was that Earth's tides were much stronger because Earth is bigger and Moon is small. And also, as they did increase the Earth-Moon mutual orbit, but by much smaller amount because Earth is big and Moon's spin was small. So this was a much faster process. The slowdown of Moon's spin, which ended up like in thousands of years maybe, has stopped lunar rotation. And for all satellites, they're small and they're close to something big, the tidal forces from the bigger body would always slow them down and make them spin synchronously. Yeah?
You're saying giant impacts account for high obliquities. Well, I heard that the high obliquity of Uranus could be, even though it's a gas planet, many scientists are attributing that to a giant impact.
Yeah, so that's something people work on. Most of Uranus is actually not gas. Like, gas is a small part of the planet, much in volume, but not much in mass. Yeah, you need to hit Uranus very fast with an Earth-sized body to produce present obliquity. It's very hard to understand because the satellites, for example, are in the equatorial plane, and if you change the equatorial plane, they will not be in the equator, or they will not be following the equator anymore, and they might actually collapse into Uranus. So yes, that is the preferred explanation, but we have loose ends. That's something people do currently work on. Yeah?
I was curious about some of the impact models, and earlier with
the various studies that are coming out, are they assuming a uniform object? In other words, that it's such and such measures of water, then such and such measures of mantle, and then such and such distance? Or are they trying to like model the, I don't know, like land on one part and sea in another part of the impact?
For the impact physics, it doesn't really matter what's in the surface. Like, you have them have atmospheres, not. It's really core in the mantle that matters. It's like the rough physics of the body. And they assume that a third of the mass is in the core, kind of like as planets usually are. So they're not assuming something strange like Mercury, which is mostly core. But yeah, the surface stuff is actually lost. So if there was a primordial atmosphere or water, much of it was lost and then came from elsewhere. Yeah.
I heard some discussion at one point about Pluto. I'd just like to know because it seems like it constantly changes around. Is Pluto a planet? Because it has moons, like Skull, but I mean, since it has moons, shouldn't it be a planet? And then again, now there's sub-moons, and I don't even know. So what is it?
Officially, it's a dwarf planet. So the question is dwarf planet a planet? You know, scientists go at each other. Like, people really get worked up about this. So, from the point of view of orbital mechanics, right? When I do simulation of the solar system, unless I care about Pluto, I usually ignore it. I go with 8 planets. So, I mean, sometimes you can go with 4. If you only care about gas giants, you have only 4 in the calculation, and then ignore Earth, and it's fine. If you're gonna do Earth and Mars, then you put in the 4 planets, and then Pluto really doesn't matter much. Now, that's it's clearly smaller than other planets. At some point, you have to say, oh, these are planets that are not. Some people think that Pluto and a bunch of other things in the Kuiper belt, like Ares, Sedna, Haumea, and so on, are planets. It's really not. Yeah. Sorry?
I was just asking about Pluto. I don't even know what it is.
Yeah. It goes around the sun. The thing has been answered before, kind of, right? So in year 1800, or 1801, sorry, from Sicily, this guy Piazzi discovered a new planet between Mars and Jupiter. So then soon people discovered a second, and then the third and the fourth. It was the first 4 asteroids. So first they called them planets, but then they were like, okay, there are too many of these things. We can't just call them planets. So they decided to call them minor planets, or asteroids. And they gave them numbers and so on. So the motions have been done before. And now, so people who do orbits usually say there are 8 planets. People who do surface geology don't care what the orbit is. It's around, it has an atmosphere, it might have moons and so on. So it's a planet. So it's really not, it's not exact, there's no exact answer. Like I can tell you what the spin period of something is or what the mass is, but is it a planet? Depends what you mean by planet.
It sounds like it's a question of opinion and not science.
Yeah, to some extent, yeah.
The definition of asteroid itself, you would define it anyway. I mean, the only reason, from what you're saying, the only reason that an asteroid itself even got defined is because there was too many of them.
Yeah, so they call them asteroids because they couldn't, so why is it called asteroid? Star-like, because they couldn't tell them apart in a telescope. It doesn't show a disk. But if you have a bigger telescope, you might be able to see something. Like Hubble Space Telescope, asteroids are not star-like. So it's all relative what you're interested in and what aspects of planets you care about.
So, in other words, I'm just trying to sum this up. In other words, the entire definition of asteroid is arbitrary.
Yeah, the definition of a planet is somewhat arbitrary, yeah. Yeah.
When you run these models, are you looking at the systems very independently? Like, do you kind of assume that there was always 8 or 9 planets for forever? Or are you doing a dance with different kinds
Well,
of...
when we do the lunar formation, then we just, we don't care where this thing came from. Kind of like, assume that it's coming from somewhere and then collide it. Now, other people try forming solar system more consistently. So usually it's assumed that the 4 giant planets were there, when the terrestrial planets formed, because it takes longer time for terrestrial planets to form. Now, we think that the gas in the protoplanetary nebula was around for a couple of millions of years, because there are many reasons for that, and the giant planets had to form by that point because they have gas. If Uranus and Neptune, for example, formed later, they would not have any gas. And then it takes longer to form terrestrial planets. So that's kind of assumptions people make. Now, also planets get moved, so there are lots of assumptions about where the giant planets were when terrestrial planets formed, and that's where the cutting edges, kind of. It looks like giant planets moved early on, and that gives us the best solution, the best results for the formation of terrestrial planets.
Does that throw off the initial conditions so much that the outcomes are like almost a guess?
Well, the outcomes are always statistical.
Okay.
So you do it lots of time. Never you're going to get the exact solar system. But, for example, you can, some initial conditions consistently give you Mars that's same size of Earth. Other will give you Mars that's often small, much smaller than Earth. So stuff like that.
Okay.
Yeah?
I guess I have two questions depending on your answer to the first one. What determines the isotope ratio? Can it be related to distance from the sun?
Probably is. We don't really understand, and in the models that I showed you, which claim that some things were likely and some were unlikely, they were different simple models where it was but it was basically depending on the distance from the sun.
Okay, so my second question, you gave the right answer. Why is it not possible then? Why are you talking about Venus and Mercury? Couldn't there be another set of gunk in space that formed the Earth and another set in the same orbit that formed this impactor, and they happened to come together and collide? They have the same isotope ratio, but they're basically the same gunk that formed each other.
Yeah, so the reason why it takes tens of millions of years for Earth or Venus to form is that they scatter the impactor. So if you have a near miss, stuff flies really far. So it takes a while for it to come back. So Earth and Venus that way are not really isolated. And that's kind of similar to the present dynamics of near-Earth asteroids. The asteroids that can hit Earth, right? If it misses Earth, it gets kicked around, might encounter Venus. So it's unlikely for stuff to stay around Earth, only Earth, and not interact with other bodies.
Maybe the impactor is at a Lagrange point on the Earth's orbit and forms separately, and they don't interact for a long time, but they form balls of the same material, same isotopic material. And then maybe Jupiter moved or kicks them into the orbit, and they then collide later. Is that possible?
People have proposed that the impactor came as a Lagrangian, like co-orbital. That means that they share the same orbit.
Yeah.
They really haven't gotten that much in simulations because this process seems to be too rough to put the body neatly into Lagrange point. People have proposed that. It's yeah, it doesn't like. Also, this isotope ratio works only for original bodies.
For what?
For original bodies, like which are much smaller than Earth. By the time you put together Earth, it's not determined only by its distance from the sun. It's by whatever random bodies it absorbed that came from different distances. Yep.
One of the last slides you showed had a bullet point that said, when the satellite impacted Earth, it made Earth grow. Can you?
Oh, that was for multiple satellites?
Okay.
No, it just means that when you have multiple impacts, sometimes satellites can, especially if you have more than one satellite, they can get on the wrong side of the spin period. That means if the satellite is going around faster than the planet spins, that means it's very close in. It can fall into the planet as opposed to. Or in this case, also if the spin and orbit axes are not well matched, there might not be enough. Like if you bring the satellite into the equatorial plane, the orbit would not be large enough because as you bring it into the plane, the orbit shrinks. So yeah, when you have multiple satellites, you can say strange things like that.
Give you with our thanks. Certificate. that has the picture of the first image, I'm sure you've seen it, of the moon, of the Earth from the moon. It was taken on Christmas Eve, Apollo 8. I'm sure we've been seeing this in television programs the last few days. And it gives a lovely image of the first one ever taken. Thank you so much for speaking to us tonight.
Thank you very much.